The speed of light isn't the cosmic speed limit. I know what you're thinking. Nothing moves faster. Einstein proved it. Case closed. Except there's something moving faster right now, something so massive it makes our entire galaxy look like a grain of sand, and it's accelerating. And here is a question. If you could witness any cosmic event in history, from the Big Bang to the death of the last star, which moment would you choose? Let us know in the comments. I'll pin the most creative answer. Now let's begin. Picture yourself standing outside on a clear night, looking up at the stars. Those pinpoints of light have traveled unimaginable distances to reach your eyes. Some of them have been journeying for billions of years. But here's where things get strange. The galaxies those stars belong to, they're moving away from us faster than light could ever travel. Not because they're breaking Einstein's rules, but because space itself is expanding, carrying everything along for the ride. This isn't some theoretical playground for physicists to amuse themselves. This is observable, measurable, documented reality. In April of 2026, just days ago, an international team of astronomers published findings showing that the universe's expansion rate sits at about 73.5 kilometers per second per megaparsec. That sounds like technical jargon, so let me translate. For every 3.3 million light-years of distance, the space between objects grows by an additional 73.5 kilometers every single second. Stack enough distance together and you get speeds that dwarf anything light can achieve. Think about that for a moment. Light travels at roughly 300,000 kilometers per second through space. But space itself? Space can stretch at whatever rate it wants. There's no speed limit on the expansion of the fabric of reality itself. It's like the difference between running on a treadmill and having the entire floor beneath you expand outward. You might be running at your maximum speed, but if the ground itself is stretching, your actual distance from your starting point grows far faster than your legs could ever carry you. The observable universe spans approximately 45 billion light-years in every direction from Earth. Wait a second, you might think. Didn't I just say the universe is around 13.8 billion years old? How can we see objects 45 billion light-years away if light has only had 13.8 billion years to travel? That's the expansion at work. While light has been traveling toward us for billions of years, the space between us and those distant galaxies has been growing the entire time. The universe pulled the cosmic rug out from under light itself. Here's where your perspective shifts. We're not at the center of anything special. There's no edge to the universe that we can point to. Every observer, everywhere in the cosmos, would see galaxies rushing away from them in all directions. An alien astronomer on a planet in the Andromeda galaxy would look out at the universe and see the same thing we do. Everything speeding away, space expanding, the cosmic horizon retreating into unreachable distance. Scientists call this the particle horizon, the cosmological horizon, or sometimes the co-moving horizon, depending on which research paper you're reading. It represents the absolute boundary of what we can observe. Beyond that distance, space expands so rapidly that light from those regions will never reach us, not in a billion years, not in a trillion, never. Those regions are fundamentally cut off from us, separated not by distance alone, but by the relentless stretching of space-time itself. And if you think that's mind-bending, we're just getting started, because the expansion of space isn't the only phenomenon that challenges everything you thought you knew about speed limits in the universe. Let me paint another picture for you. Imagine two particles, perhaps electrons, born from the same quantum event. These particles become entangled, linked in a way that defies our everyday intuition. Change the state of one particle and the other responds instantaneously, regardless of the distance separating them. You could place one particle here on Earth and send the other to the edge of the galaxy, and they would still remain connected. Measure the spin of one, and you instantly know the spin of the other. Albert Einstein famously called this spooky action at a distance, and he wasn't comfortable with it. It seemed to violate the cosmic speed limit he himself had established. But experiment after experiment has confirmed that quantum entanglement is real. It happens. It's not magic, and it's not a mistake. It's a fundamental feature of quantum mechanics, woven into the very fabric of reality. Now here's the critical part that trips people up. Quantum entanglement doesn't allow for faster-than-light communication. You can't use it to send messages or information across space instantaneously. The correlation between entangled particles is real, but you can't control what state either particle takes when you measure it. You only know that the states will be correlated. Think of it like this. Imagine you and a friend each have a mystery box. When you open yours and find a red ball, you instantly know your friend's box contains a blue ball. But you didn't send any information, you just learned something about a connection that already existed. Still, the speed at which this correlation manifests? That part is instantaneous, or at least absurdly fast. Recent experiments in 2026 measured quantum entanglement forming in attoseconds. An attosecond is 1/1000th of a second. To give you perspective, light takes about 0.3 attoseconds to cross a single hydrogen atom. These researchers used incredibly precise laser pulses on helium atoms and tracked the exact moment when entanglement formed between electrons. The process happens faster than anything we can directly observe with conventional technology. Understanding these timescales could revolutionize quantum computing, cryptography, and secure communications. If we can control when and how entanglement forms with attosecond precision, we might unlock technologies that seem impossible today. Quantum computers that solve problems in seconds that would take classical computers millennia. Encryption systems that are fundamentally unbreakable. Communication networks where information security is guaranteed by the laws of physics themselves. But let's zoom back out for a moment, because there's something even stranger happening in the universe's grand story, something that ties all of this together. If you're finding this fascinating, give this video a like and hit that subscribe button. Your support helps me bring more of these cosmic journeys to you. Dark energy. Two words that represent one of the most profound mysteries in all of science. We don't know what it is, we don't know where it comes from, but we know it's out there, and it's pushing the universe apart at an accelerating rate. This invisible force makes up approximately 68% of everything that exists. You, me, the planets, stars, galaxies, all the matter we can see and touch, that accounts for less than 5% of the universe. The rest is dark energy and dark matter, and dark energy is winning. Here's what that means in practical terms. 100 years ago, astronomers discovered that distant galaxies were moving away from us. Edwin Hubble, using the 100-inch telescope at Mount Wilson Observatory, measured the redshift of galaxies and realized the universe was expanding. That was revolutionary enough, but in 1998, two independent teams of astronomers studying distant supernovae made an even more shocking discovery. The expansion wasn't slowing down as everyone expected, it was speeding up. Imagine throwing a ball into the air and watching it accelerate upward instead of falling back down. That's essentially what the universe is doing. Some mysterious force is pushing against gravity, driving galaxies apart faster and faster with each passing moment. We call this force dark energy, but that's just a placeholder name for we honestly have no idea what this is. The leading model, called lambda CDM, incorporates dark energy as a cosmological constant, a sort of intrinsic energy of empty space itself. Einstein actually proposed something similar over a century ago, then called it his greatest blunder when he thought the universe was static. Turns out he might have been onto something after all, but even our best models leave enormous questions unanswered. Why does dark energy have the precise value it does? Why is it causing the acceleration we observe rather than some other effect? Is it truly constant, or does it change over time? These aren't just academic puzzles. They determine the ultimate fate of the universe itself. If dark energy continues accelerating the expansion, eventually galaxies beyond our local group will recede so far and so fast that their light will never reach us. The night sky will grow darker over trillions of years as one by one the galaxies wink out, not because they've died, but because they've crossed beyond the cosmic horizon. Future civilizations, if any exist, will look up and see almost nothing. They'll have no way to know that billions of other galaxies once filled the universe. Their entire observable cosmos will consist of whatever stars remain in their local gravitational neighborhood. Some cosmologists call this the Big Freeze or heat death. Others propose more dramatic scenarios. If dark energy's strength increases over time, it could eventually overcome not just the gravity holding galaxy clusters together, but the forces binding galaxies themselves, then solar systems, then planets, then atoms. This theoretical end state is called the Big Rip, where the fabric of space-time tears itself apart, shredding everything down to the quantum level. Current observations suggest this probably won't happen, but we can't rule it out completely. The universe still holds its cards close. Now let's connect this back to the speed of light. As dark energy pushes space to expand faster and faster, more and more of the universe crosses beyond our cosmic horizon. Right now, there are galaxies receding from us at several times the speed of light. Not because they're moving through space that fast, but because the space between us and them is expanding at that rate. Einstein's theory of relativity says nothing can move through space faster than light, but it places no restriction on how fast space itself can grow. This might sound like a technicality, some kind of cosmic loophole, but it has real consequences. There's a sphere around Earth, roughly 15 billion light-years in radius, called the Hubble sphere. Objects beyond that distance are receding from us faster than the speed of light due to cosmic expansion. We can still see many of them because they emitted their light when they were closer, and the expansion rate was slower, but anything currently beyond the Hubble sphere that hasn't already sent light our way, we'll never see it, ever. Speaking of cosmic speeds and perspectives, if you're curious about how fast we're actually moving through space, considering Earth's rotation and the galaxy's motion through the universe, I made a detailed video exploring exactly that. It's called How Fast Are We Actually Moving Through Space? And you'll find it linked in the description. Trust me, the answer will surprise you. But let's return to our main story, because there's another phenomenon that challenges our understanding of cosmic speed limits, and this one happens not in the vast distances between galaxies, but in the smallest realms of existence. Phase velocity. This is a concept from wave physics, and it describes how fast the peaks and troughs of a wave pattern move through space. Here's the wild part. Phase velocity can exceed the speed of light without violating relativity. I know, that sounds impossible, but stay with me. When waves interact with certain materials or propagate through specific mediums, the pattern they create can appear to move faster than light. The key word there is appear. No actual information or energy travels faster than light in these cases. It's the pattern itself, the relationship between wave peaks that shifts at superluminal speeds. Think of it like a stadium wave at a sports event. The wave pattern races around the stadium far faster than any individual person could run, but no actual person is moving at that speed. Everyone just stands and sits in sequence, creating the illusion of rapid movement. Scientists have demonstrated this in laboratory settings using carefully controlled laser pulses passing through specially prepared atomic vapors. The peak of the pulse can exit the medium before it enters, which sounds like time travel, until you realize that no information has actually moved backward in time. The pulse gets reshaped by its interaction with the atoms in ways that make the peak shift forward. It's a weird quantum mechanical effect, but it doesn't let you send messages to the past or violate causality. Similarly, astronomers observe superluminal motion in certain astronomical jets. When material shoots out from the vicinity of a supermassive black hole at speeds approaching that of light, and the jet happens to point almost directly toward Earth, a geometric projection effect makes the material appear to move across the sky faster than light. Again, this is an illusion created by the specific viewing angle and the incredible speeds involved, not actual faster-than-light travel. These phenomena remind us that the universe is full of situations where our intuitive understanding breaks down. What seems impossible often turns out to be perfectly consistent with physics once you dig into the details. The speed of light remains the ultimate limit for information transfer, for cause and effect, for anything that could allow you to send a signal from one point to another. But the universe has found numerous creative ways to seem like it's breaking that rule without actually doing so. And then there's the quantum vacuum itself, which is far from empty. Pop quiz. What's in the space between atoms? Most people would say nothing, maybe vacuum, perhaps empty space. All of those answers are wrong. Quantum field theory tells us that the vacuum is seething with activity. Particle-antiparticle pairs spontaneously pop into existence, borrow energy from the quantum uncertainty principle, exist for impossibly brief moments, and then annihilate back into nothingness. This happens everywhere, all the time, at scales too small and too fast for us to directly observe. These aren't just theoretical constructs, they have measurable effects. The Casimir effect, for instance, arises when two metal plates are placed extremely close together in a vacuum. The quantum fluctuations between the plates are restricted compared to the fluctuations outside, creating a net force that pushes the plates together. Scientists have measured this force in laboratories. It's real. The vacuum has structure, has energy, has properties that influence the behavior of matter and light. Some physicists speculate that these quantum vacuum fluctuations might even be connected to dark energy, that the energy inherent in empty space could be driving cosmic acceleration. The math doesn't quite work out yet. In fact, when you calculate what the vacuum energy should be based on quantum mechanics, you get an answer that's wrong by a factor of 10 to the power of 120, possibly the worst prediction in the history of physics. But the underlying intuition might still be pointing in the right direction. We just don't understand it yet. This is where science gets exciting. Where the boundaries of knowledge become visible, we have incredible theories that explain vast swaths of reality with stunning precision. General relativity predicts the behavior of black holes, gravitational waves, the bending of light around massive objects. Quantum mechanics explains atoms, chemistry, the behavior of electrons in computer chips. Both theories have been tested countless times and passed every experimental challenge we've thrown at them. Yet they don't play nicely together. At the extreme scales where both quantum effects and gravity become important, the centers of black holes, the first moments of the Big Bang, our equations break down. We need a theory of quantum gravity, a framework that unifies these two pillars of modern physics. String theory, loop quantum gravity, and other approaches have made progress, but we don't yet have a complete, tested theory that works. This brings us to something that sounds like pure science fiction, but might be woven into the very structure of reality: cosmic inflation. In the first tiny fraction of a second after the Big Bang, something extraordinary happened. The universe didn't just expand, it exploded outward at speeds that make our current cosmic expansion look glacial by comparison. During a period lasting perhaps 10 to the power of negative 34 seconds, the universe grew by a factor of at least 10 to the power of 26. That's expanding from smaller than a subatomic particle to roughly the size of a grapefruit, or possibly much larger, in less time than it takes light to cross the nucleus of an atom. This is inflation, and it happened faster than light could possibly travel, way faster. The expansion during inflation was so rapid that regions of space that had been in contact, able to exchange energy and information, suddenly found themselves separated by distances so vast that light hasn't had enough time to travel between them even now, nearly 14 billion years later. This explains one of the biggest puzzles in cosmology. Why does the universe look essentially the same in every direction we look, even in regions that should never have been able to influence each other? The answer is that they were in contact before inflation ripped them apart. The entire observable universe, everything we can see with our most powerful telescopes, came from a region smaller than a single atom. Inflation stretched that tiny patch of space, smoothing out any irregularities, creating the remarkably uniform cosmos we inhabit. But it didn't smooth everything perfectly. Quantum fluctuations in that primordial patch got inflated along with everything else, and those microscopic variations became the seeds of every galaxy, star, and planet that would ever form. We have evidence for inflation written across the sky. The cosmic microwave background radiation, that faint glow of heat left over from when the universe first became transparent to light, shows a pattern of hot and cold spots that matches the predictions of inflation theory almost perfectly. Missions like COBE, WMAP, and Planck have mapped this ancient light in exquisite detail, and the data keeps supporting the inflationary model. But here's what keeps cosmologists up at night. We don't know what caused inflation. We don't know what the inflaton field is, if that's even the right way to think about it. We have mathematical models that work, equations that match observations, but the underlying mechanism remains mysterious. Some versions of inflation predict a multiverse, an infinite number of separate universes beyond our cosmic horizon, each potentially with different physical laws and constants. Other versions suggest inflation might still be happening in distant regions of space-time, eternally spawning new universe bubbles. These ideas push the boundaries of what we can call science. If other universes exist but are forever beyond our ability to observe or interact with them, can we meaningfully say they're real? This gets into philosophy as much as physics, and scientists have passionate disagreements about where the line should be drawn. What we can say with confidence is this: the early universe expanded faster than light. The current universe is expanding faster than light at sufficiently large distances, and these facts don't contradict relativity because the speed limit applies to motion through space, not the expansion of space itself. It's a crucial distinction, one that opens up the cosmos in ways that would be impossible if light speed were truly the ultimate limit on everything. Now let me tell you about something even stranger, something happening right now in laboratories and in the depths of space: Cherenkov radiation. You might have seen pictures of nuclear reactors with that characteristic blue glow surrounding the fuel rods. That's Cherenkov radiation, and it happens when particles travel through a medium faster than light can travel through that same medium. Wait, didn't I just say nothing can travel faster than light? Here's the nuance. The speed of light in vacuum is the ultimate speed limit, but light slows down when traveling through materials. In water, light moves at about 75% of its vacuum speed. In glass, it's even slower. High-energy particles, like electrons produced by radioactive decay, can absolutely move faster than light travels through water or glass, while still moving slower than light would in vacuum. When they do, they produce this beautiful blue glow, Cherenkov radiation, as they create a kind of optical shock wave. This same phenomenon happens in space. When ultra-high energy cosmic rays, particles accelerated to incredible speeds by supernovae or black holes or still mysterious sources, slam into Earth's atmosphere, they can briefly move faster than light travels through air. The resulting Cherenkov radiation cascades down through the atmosphere, and we've built detectors specifically to catch these flashes of blue light. Arrays of telescopes like Veritas, HESS, and the Cherenkov Telescope Array scan the night sky looking for these events, using them to trace cosmic rays back to their sources. These cosmic rays themselves represent another challenge to our understanding. The most energetic ones carry as much kinetic energy as a well-thrown baseball, except all that energy is packed into a single atomic nucleus. We call them ultra-high energy cosmic rays, and we have no idea how nature accelerates particles to such extreme speeds. The most powerful particle accelerator humans have ever built, the Large Hadron Collider, reaches energies around 10 to the power of 13 electron volts. These cosmic rays can exceed 10 to the power of 20 electron volts. Something out there is running a particle accelerator millions of times more powerful than anything we can construct. Supermassive black holes are prime suspects. When material spirals into a black hole, it forms an accretion disk, a swirling maelstrom of superheated gas and plasma. Magnetic fields threading through this disk can channel particles outward in jets that extend for thousands or even millions of light years. These jets glow brilliantly across the electromagnetic spectrum, visible in radio waves, optical light, X-rays, and gamma rays. The particles within them reach speeds of 99.9% the speed of light or even closer. One particularly famous example is the galaxy M87, the same galaxy where astronomers used the Event Horizon Telescope to capture the first ever image of a black hole's shadow in 2019. That black hole is launching a jet of material that extends more than 5,000 light-years into space. We can watch this jet evolve over time, see bright knots of material racing outward at apparent speeds several times the speed of light. Again, this is a projection effect, not actual faster-than-light motion, but it demonstrates the mind-boggling energies at play near supermassive black holes. Speaking of black holes, let's talk about what happens at their event horizons. This is the point of no return, the boundary where escape velocity exceeds the speed of light. Once something crosses the event horizon, not even light can escape. It's gone from our universe, effectively erased from the cosmic ledger. But here's the weird part. From the perspective of someone watching from a safe distance, anything falling toward a black hole appears to slow down as it approaches the event horizon, getting dimmer and redder, asymptotically approaching but never quite reaching the boundary. This isn't an illusion. Time itself dilates near massive objects, as predicted by general relativity and confirmed by countless experiments. Clocks run slower in strong gravitational fields. For the infalling observer, they cross the event horizon in finite time and continue falling toward the singularity at the black hole's center. But for the external observer, that crossing takes, literally, forever. Both perspectives are equally valid. This is the relativity in relativity. Different reference frames experience time and space differently, and there's no universal privileged viewpoint. At the singularity itself, assuming one exists, the curvature of space-time becomes infinite. Densities become infinite. Our equations produce infinities, which is physics speak for we don't know what happens here. Most physicists suspect that quantum gravity effects become important at these scales, preventing true infinities from forming. Maybe the singularity is replaced by some kind of quantum foam or Planck scale structure. Maybe black holes are actually fuzzballs of string theory, or gravastars, or something we haven't even imagined yet. What we do know is that black holes emit Hawking radiation, a prediction made by Stephen Hawking in 1974. Quantum effects near the event horizon allow particle pairs to form, and occasionally one particle falls into the black hole while the other escapes. To an external observer, the black hole appears to emit thermal radiation. The smaller the black hole, the hotter this radiation. Supermassive black holes emit Hawking radiation at temperatures far below the cosmic microwave background, so they're actually absorbing more energy than they emit. But microscopic black holes, if any exist, would glow white hot and evaporate in fractions of a second. This process demonstrates quantum entanglement on cosmic scales. The particles that escape are entangled with the particles that fell in, creating what's known as the black hole information paradox. When a black hole eventually evaporates completely, what happens to the information about everything that fell in? Does it disappear, violating quantum mechanics? Does it get encoded in the Hawking radiation somehow? Does it leak out through wormholes to baby universes? Physicists have debated this for decades, and while recent work suggests the information is preserved in subtle correlations in the radiation, the exact mechanism remains controversial. These questions aren't just abstract philosophy, they probe the deepest foundations of reality, the interplay between quantum mechanics, thermodynamics, and gravity. Understanding black holes fully requires understanding quantum gravity, and that remains one of the greatest unsolved problems in theoretical physics. Now let's shift our focus to something you can actually see, something that connects the cosmic speed limit to everyday technology, your GPS. Every time you use navigation on your phone, you're relying on Einstein's theory of relativity. The satellites orbiting Earth that provide your location are moving at about 14,000 kilometers per hour and experiencing weaker gravity than you are on the surface. Both of these factors affect how fast time passes for the satellite clocks compared to clocks on the ground. Special relativity tells us that moving clocks tick slower. The GPS satellites are moving fast enough that their clocks lose about 7 microseconds per day compared to stationary clocks on Earth. But general relativity tells us that clocks in weaker gravitational fields tick faster. The satellites are high enough above Earth that this effect gains them about 45 microseconds per day. The net result is that satellite clocks run about 38 microseconds faster than ground clocks each day. That might not sound like much, but light travels about 30 centimeters in 1 nanosecond. 38 microseconds is 38,000 nanoseconds. Without correcting for relativistic effects, GPS would accumulate errors of about 10 kilometers per day. Your navigation system would be essentially useless. Engineers have to program the satellite clocks to tick at a slightly different rate to compensate for these relativistic effects. Every time you get accurate directions to your destination, you're experiencing proof that Einstein was right about the nature of space and time. This same relativistic framework explains why particle accelerators work the way they do. At the Large Hadron Collider, protons race around a 27-kilometer ring at 99.999991% the speed of light. At those speeds, the protons experience time dilation by a factor of about 7,500. From the proton's perspective, it takes much less time to complete each lap than we measure from our reference frame. This allows particles to travel distances that would be impossible at slower speeds before they decay. In fact, this effect is visible in cosmic rays hitting Earth's atmosphere. Muons, unstable particles created when cosmic rays collide with air molecules, have an average lifetime of about 2 microseconds before decaying. At near light speed, muons created in the upper atmosphere should only travel about 600 meters before decaying, nowhere near enough to reach the ground. Yet we detect muons at sea level all the time. How? Time dilation. From the muon's perspective, its lifetime is still 2 microseconds, but from our perspective, that lifetime is stretched by a factor of dozens or even hundreds, depending on the muon's speed. The muon experiences the atmosphere as compressed in the direction of motion, so it doesn't need as much time to traverse it. This is the reality of living in a relativistic universe. Time and space aren't fixed, absolute backgrounds. They're flexible, malleable, intimately connected to motion and gravity. Einstein showed us that space and time are actually one unified entity, space-time, and massive objects warp its geometry the way a bowling ball creates a dip in a stretched rubber sheet. Gravitational waves are ripples in this space-time fabric. When massive objects like black holes or neutron stars orbit each other and eventually merge, they create disturbances that propagate outward at exactly the speed of light. These waves compress and stretch space itself as they pass through, changing the distance between objects by tiny, tiny amounts. LIGO, the Laser Interferometer Gravitational Wave Observatory, detected the first gravitational waves in September of 2015, confirming a prediction Einstein made a century earlier. The detection was absurdly difficult. The gravitational wave from the black hole merger that LIGO observed changed the length of the detector's 4-kilometer arms by about 1/10,000th the width of a proton. Imagine measuring a change in the distance to the nearest star that's smaller than the width of a human hair. That's the level of precision required. The scientists and engineers who built LIGO essentially created the most sensitive measurement device in human history. Since that first detection, LIGO and its European counterpart Virgo have observed dozens of gravitational wave events, black hole mergers, neutron-star mergers, and exotic events we're still trying to fully understand. In August of 2017, LIGO and Virgo detected gravitational waves from colliding neutron stars, and within seconds, telescopes around the world turned to observe the same event in visible light, X-rays, gamma rays, and radio waves. This multi-messenger astronomy opened an entirely new way of studying the universe. That neutron-star merger produced heavy elements like gold, platinum, and uranium through rapid neutron capture, a process called R-process nucleosynthesis. The atoms in any gold jewelry you own were likely forged in similar cataclysmic collisions billions of years ago, scattered through space by the explosion, eventually incorporated into the cloud of gas that formed our solar system. You are literally wearing pieces of dead stars, tangible connections to events of unimaginable violence and beauty. This is what I mean by the human connection to the cosmos. Every atom in your body, heavier than helium, was created inside a star. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it synthesized in stellar furnaces or explosive stellar deaths. Carl Sagan famously said we're made of star stuff, and he meant it literally. You are the universe experiencing itself, a temporary arrangement of particles that once existed in completely different forms, scattered across light years of space, now assembled into a conscious being capable of contemplating its own origins. Think about that for a moment. The atoms forming your brain right now might have been part of different stars, ejected by different supernovae, traveling through interstellar space for millions or billions of years before gravity collected them into the molecular cloud that birthed our sun. Those atoms have histories. They've witnessed cosmic epochs you can barely imagine. And now they're arranged in patterns complex enough to generate thoughts, emotions, curiosity, wonder. This perspective shift is what astronomy offers. It's not just about learning facts and figures, though those are important. It's about understanding your place in the grand cosmic story, recognizing that you're part of something vastly larger than yourself, while simultaneously being utterly unique. There has never been and will never be another arrangement of atoms exactly like you. You are a fleeting pattern in the cosmic dance, temporary but meaningful, ephemeral but beautiful. Now let's return to the question of cosmic speed limits, because there's another phenomenon worth exploring: tachyons. These are hypothetical particles that would always travel faster than light, existing permanently in the superluminal realm. If they exist, and there's absolutely no evidence that they do, they would have imaginary mass, which doesn't mean made up, but rather involves the square root of negative numbers. Their behavior would be bizarre and paradoxical from our perspective. A tachyon moving away from you would appear to gain energy as it slows down, and it would have to expend energy to speed up. The faster it goes, the less energy it carries. At infinite speed, it would have zero energy. This is completely backward from normal particles, where faster means more energetic. Tachyons would also potentially allow for causality violations, situations where effects precede causes, which opens up all sorts of logical paradoxes. Most physicists don't think tachyons exist. They're mathematically possible in certain formulations of relativistic physics, but that doesn't mean nature actually uses them. Lots of things are mathematically consistent but don't correspond to reality. We could write equations describing universes with 17 spatial dimensions, or where gravity is repulsive instead of attractive, but that doesn't make those universes real. What is real, however, is the ongoing tension between quantum mechanics and relativity, and the search for a theory that unifies them. String theory proposes that the fundamental constituents of reality aren't point-like particles, but tiny vibrating strings of energy. Different vibration patterns correspond to different particles. An electron is one vibration mode, a quark is another, a photon is yet another. Gravity itself emerges from a particular string vibration pattern called the graviton. String theory requires extra dimensions of space beyond the 3 we experience. Depending on the version, you need 10 or 11 total dimensions for the mathematics to work. The extra dimensions are supposedly curled up so small we can't detect them, existing at scales near the Planck length, about 10 to the power of negative 35 meters. At those scales, quantum fluctuations of spacetime itself become significant, and our classical notions of smooth, continuous space break down. Loop quantum gravity takes a different approach. Instead of adding extra dimensions, it quantizes spacetime itself, proposing that space and time come in discrete chunks at the Planck scale. Spacetime would be granular, like a fabric woven from quantum threads rather than smooth and continuous. In this picture, the geometry of space is dynamic and evolves according to quantum rules. Both approaches have strengths and weaknesses. String theory makes contact with particle physics naturally and includes gravity, but it hasn't yet made testable predictions that distinguish it from other theories. Loop quantum gravity avoids some of the mathematical infinities that plague quantum field theory in curved spacetime, but it hasn't successfully incorporated all the particles and forces we observe. The honest truth is, we don't know which approach, if either, will ultimately succeed. What we do know is that somewhere in the universe's story, quantum gravity becomes essential. The first instant of the Big Bang, the singularity at the heart of a black hole, maybe even certain configurations of matter at extreme densities, all of these situations demand a theory that seamlessly blends quantum mechanics and general relativity. Without it, we're working with incomplete maps, trying to navigate territory our current theories can't fully describe. Consider what happened in the first moments after the Big Bang. At the Planck time, about 10 to the power of negative 43 seconds after the initial event, the universe was so hot and dense that all 4 fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified into a single force. We have no tested theory that describes physics under those conditions. Our equations literally don't work. The temperature was about 10 to the power of 32 Kelvin, hot enough that particle energies exceeded the Planck energy, the scale where quantum gravitational effects dominate. As the universe expanded and cooled, These forces separated out one by one. Gravity split off first, then the strong nuclear force, then at much lower energies, electromagnetism, and the weak force separated. By the time the universe was about 1 microsecond old, it had cooled enough for quarks to bind together into protons and neutrons. At 3 minutes old, nuclear fusion began creating the first helium and lithium nuclei. At 380,000 years old, electrons combined with nuclei to form the first atoms, and the universe became transparent to light for the first time. That light has been traveling through space ever since, stretched by cosmic expansion into the microwave part of the spectrum. The cosmic microwave background represents our oldest baby picture of the universe, a snapshot of what things looked like when the cosmos was less than 1/400,000th its current age. Every direction you look, you're seeing ancient light that has traveled for over 13 billion years to reach your eyes. Or rather, to reach our telescopes, since this light has been redshifted far beyond what human eyes can detect. The pattern of hot and cold spots in this ancient light encodes information about the universe's composition, age, and geometry. It tells us the universe is flat or very close to it, meaning parallel lines stay parallel forever rather than converging or diverging. It tells us exactly how much ordinary matter exists, how much dark matter, and how much dark energy. The precision of these measurements is remarkable. We know the universe is 13.77 billion years old, give or take 40 million years. That's uncertainty of less than 1%. Yet despite this precision, fundamental mysteries remain. Why does dark matter interact gravitationally but not electromagnetically? What particle or particles constitute dark matter? We've built incredibly sensitive detectors deep underground, shielded from cosmic rays, searching for the faint signal of a dark matter particle colliding with ordinary matter. So far, nothing. We've searched for dark matter at the Large Hadron Collider. Nothing. We've looked for indirect signatures in cosmic rays and gamma rays from space. Tantalizing hints, but nothing confirmed. The leading candidate for years was something called a WIMP, a weakly interacting massive particle. These hypothetical particles would have masses tens or hundreds of times heavier than a proton and would interact through gravity and the weak nuclear force but not electromagnetism or the strong force. They'd pass through ordinary matter almost like ghosts, occasionally colliding with an atomic nucleus in a detectable way. But despite decades of searching with ever more sensitive experiments, we haven't found them. Alternative candidates exist. Axions, extremely light particles originally proposed to solve a problem in quantum chromodynamics, could constitute dark matter if they exist in sufficient quantities. Sterile neutrinos, hypothetical cousins of the known neutrinos that don't interact via any force except gravity, are another possibility. Some physicists have proposed that dark matter isn't a particle at all, but rather a modification to how gravity works at large scales. This approach, called modified Newtonian dynamics or MUN, can explain some observations but struggles with others. The truth is, we're still gathering clues. Dark matter affects how galaxies rotate, how galaxy clusters hold together, how light bends around massive structures, and how the universe evolved from the nearly smooth plasma of the early cosmos to the rich web of galaxies we see today. It's clearly there, doing something important. We just don't know what it is yet. This uncertainty might frustrate you, and honestly, it frustrates scientists too. But it's also exhilarating. We're living in an era where some of the biggest questions about the universe remain unanswered. Future discoveries could come from anywhere: a particle detector in Antarctica, a telescope on a mountaintop in Chile, a satellite orbiting Earth, or a brilliant theoretical insight from someone working in a university office. The next breakthrough might happen tomorrow, or it might take decades. That's the nature of scientific exploration. Now I want to circle back to something we touched on earlier, the cosmic horizon and what it means for the future. The observable universe has a finite size, not because the universe itself is finite, but because light has only had a finite time to travel since the Big Bang. As time passes, we can see farther and farther as light from more distant regions reaches us. You might think this means the observable universe is getting bigger, and you'd be partly right, but there's a twist. Because of dark energy accelerating the expansion, there's a limit to how much more we'll ever be able to see. Regions of space currently beyond a certain distance are receding so fast that light leaving them now will never reach us. The expansion of space between here and there is outpacing light's journey toward us. These regions are crossing out of our causal future. We can see light they emitted in the past when they were closer, but anything happening there now is forever unobservable. This means the universe has an event horizon similar to a black hole's event horizon, but inverted. Instead of a boundary where things can go in but not out, it's a boundary beyond which information can never reach us. The universe beyond our cosmic horizon is like a foreign country we can never visit, never communicate with, never influence or be influenced by. It exists, at least we have every reason to think it does, but it's fundamentally disconnected from our observable universe. Over trillions of years, as dark energy continues to dominate, this event horizon will actually shrink in cosmic terms. More and more galaxies will cross beyond it, winking out of view one by one. Eventually, in the unimaginably distant future, only the galaxies in our local gravitationally bound group will remain visible. The local group, consisting of the Milky Way, Andromeda, and a few dozen smaller galaxies, will merge into a single, giant, elliptical galaxy. The sky will be mostly dark, with far fewer stars than we see today, as star formation gradually consumes all available gas. The last stars will burn out. White dwarfs will cool to black dwarfs. Neutron stars will radiate away their remaining heat. Black holes will slowly evaporate through Hawking radiation. After 10 to the power of 100 years or so, even the black holes will be gone, and the universe will consist of nothing but a thin, cold soup of photons and the lightest particles, separated by ever-increasing distances. This is the heat death, the ultimate fate of the cosmos according to our current understanding. It sounds bleak, and in a sense it is, but there's also something poetic about it. The universe began in a state of incredible uniformity, a hot, dense plasma with barely any structure. Through gravity, quantum fluctuations, and the interplay of forces, that simple initial state evolved into galaxies, stars, planets, life, consciousness, art, music, love, everything that makes existence meaningful. And then, over time scales that dwarf the current age of the universe by factors of trillions upon trillions, it all gradually winds down, returning to simplicity. From uniformity to complexity and back to uniformity. A cosmic story with a beginning, a middle full of drama and wonder, and an ending of quiet emptiness. But here's the thing, that ending is so far in the future that it's almost meaningless to our lives. The Sun has about 5 billion years of stable burning left. Earth will remain habitable for perhaps another billion years before increasing solar luminosity makes the oceans evaporate. Humanity has existed in its current form for only about 300,000 years. Recorded civilization is less than 10,000 years old. We are living in the universe's youth, in an era of abundant stars and galaxies, of ongoing cosmic drama, of possibilities we're only beginning to explore. The fact that the universe will eventually grow cold and dark doesn't diminish the beauty and significance of now. If anything, it makes this moment more precious. We exist in a brief window of cosmic history where stars shine, where planets orbit them, where complex chemistry can create life, where conscious beings can look up at the night sky and ask questions about their origins and their fate. That's a gift, a stroke of incredible fortune in the grand scheme of things, and we're making the most of that gift. Right now, at this very moment, robotic spacecraft are exploring our solar system in ways that would have seemed like pure fantasy just a generation ago. The James Webb Space Telescope is peering back to when the first galaxies formed, capturing images of structures that existed when the universe was only a few 100 million years old. The Perseverance rover is collecting samples on Mars that might contain evidence of ancient microbial life. The Europa Clipper mission is on its way to Jupiter's moon Europa, where a global ocean beneath an icy shell might harbor living organisms. These aren't just machines gathering data, they're extensions of human curiosity, our desire to understand, our need to explore. Every image they send back, every measurement they take, expands our understanding of what's possible in this universe. When Voyager 1 crossed into interstellar space in 2012, it carried with it a golden record containing sounds and images from Earth, a message to any civilization that might find it billions of years from now. Even if that message is never received, the act of sending it matters. It says, "We were here, we wondered about the universe, and we hope to connect with others who might share that wonder." The search for extraterrestrial intelligence continues through projects like SETI, the Search for Extraterrestrial Intelligence. Radio telescopes scan the sky looking for signals that might indicate technological civilizations on distant worlds. So far, we've heard nothing but cosmic static, the natural emissions from stars and pulsars and gas clouds, but the search has barely begun. We've examined only a tiny fraction of the sky at a limited range of frequencies, looking for specific types of signals. The universe could be teeming with intelligent life using communication methods we haven't thought to search for. The famous Fermi paradox asks why, if intelligent life is common, we haven't seen any evidence of it. The galaxy is over 13 billion years old. Even with slower-than-light travel, a spacefaring civilization could colonize the entire galaxy in just a few million years. So where is everybody? Proposed solutions range from the depressing, intelligent life is extremely rare or tends to destroy itself quickly, to the intriguing advanced civilizations deliberately avoid contact or use communication methods we can't detect or exist in forms we wouldn't recognize. Perhaps the speed of light truly is an insurmountable barrier for interstellar civilizations, making the galaxy effectively too large to cross in practical terms. The nearest star system, Alpha Centauri, is about 4.3 light-years away. With current technology, a spacecraft would take tens of thousands of years to get there. Even with significant advances in propulsion, even reaching a substantial fraction of light speed, the journey would span decades or centuries. The distances are just so vast, yet there's a concept called relativistic time dilation that offers a potential workaround, not for the journey time as measured by those left behind, but for the travelers themselves. If you could accelerate a spacecraft to 99.99% of light speed, time aboard the ship would slow down dramatically relative to the rest of the universe. A journey that takes 40 years for observers on Earth might feel like only 1 or 2 years to the crew. Push even closer to light speed, and you could theoretically cross the entire galaxy in a human lifetime, from the perspective of the travelers. Of course, the energy requirements are staggering. Accelerating even a small spacecraft to such speeds would require more energy than humanity currently produces in years or decades. You'd need some revolutionary propulsion system, perhaps a fusion rocket or antimatter engine, or a light sail pushed by powerful lasers, or something we haven't even conceived yet. And then there's the problem of colliding with interstellar dust and gas at relativistic speeds. At those velocities, even a speck of dust carries enormous kinetic energy and could catastrophically damage a spacecraft. These challenges are immense, but they're engineering challenges, not fundamental impossibilities. The The laws of physics don't forbid interstellar travel, they just make it really, really difficult. Maybe civilizations that last long enough and develop sufficiently advanced technology can overcome these obstacles. Or maybe the distances are too great, the energy costs too high, the time investments too lengthy for any civilization to bother. Maybe intelligent life arises, flourishes for a time, and then dies out, all without ever making contact with neighbors separated by dozens or hundreds or thousands of light years. This is one of the deep implications of light speed being the cosmic speed limit. It fragments the universe into isolated pockets, regions that can in principle communicate, but in practice might never do so because of the sheer scale involved. If there's a thriving civilization around a star 5,000 light-years away, a signal we send now won't reach them for 5,000 years, and their reply won't get back to us for another 5,000 years, 10,000 years of round-trip communication time. That's longer than recorded human history. It's difficult to maintain continuity of purpose across such spans. Yet radio waves travel at light speed, making them our fastest method of sending information across cosmic distances. The first radio broadcast strong enough to leak into space happened in the early 20th century. Those signals are now expanding outward in a sphere roughly 120 light-years in radius, carrying I Love Lucy episodes and news broadcasts and World War II propaganda into the cosmos. Any civilization within that sphere, with sensitive enough receivers pointed in the right direction at the right time, could detect those signals and know that Earth harbors technological intelligence. Of course, the signals are incredibly faint by the time they've traveled dozens or hundreds of light years, diluted by the inverse square law, scattered and absorbed by interstellar gas. Detecting them would require radio telescopes far more sensitive than anything we've built. But it's possible in principle our presence is slowly being advertised to the galaxy whether we intend it or not. Some scientists worry about this. If hostile civilizations exist, broadcasting our location might be dangerous. Others argue that any civilization capable of crossing interstellar space to reach us wouldn't need our radio signals to find us. They could detect Earth's atmospheric composition, the presence of oxygen and methane in ratios that suggest biological activity, without needing to pick up our television broadcasts. We're already visible to anyone looking carefully enough. Personally, I find the idea that we're alone in the universe harder to believe than the idea that life is common. The universe contains at least 200 billion galaxies, each with hundreds of billions of stars. Even if only a tiny fraction of those stars have planets, and only a tiny fraction of those planets are in the habitable zone, and only a tiny fraction of those develop life, and only a tiny fraction of those develop intelligent life, the numbers are still staggering. There should be millions or billions of worlds with life, potentially thousands with technological civilizations. But maybe intelligence is rarer than we think. Maybe the jump from simple microbial life to complex multicellular organisms is unlikely. Maybe the development of technology requires a very specific set of circumstances that don't often occur. Or maybe we're actually among the first. The universe is 13.77 billion years old, but the first generation of stars contained no heavy elements, making planets and chemistry, as we know them, impossible. It took billions of years of stellar evolution to enrich the cosmos with carbon, oxygen, nitrogen, iron, all the elements necessary for life. Perhaps we live in the early era when intelligent life is just beginning to emerge. That's both humbling and exhilarating. If we're early, we have a responsibility to survive, to spread beyond Earth, to ensure that intelligence persists in the universe. Because if we fail, if we destroy ourselves through war or environmental collapse or any of the various catastrophes we're capable of inflicting, we might be snuffing out one of the first sparks of consciousness the universe has produced. This brings us back to perspective. You are part of something unimaginably vast and ancient. The atoms in your body were forged in stellar furnaces billions of years ago. They've traveled across light years of space, witnessed the birth and death of worlds, and now they're assembled into you, into a being capable of understanding this cosmic heritage. You're a way for the universe to know itself, to reflect on its own existence. That's not mysticism, that's literal fact. And yet, despite all we've learned, despite telescopes that can see nearly to the edge of the observable universe, despite equations that predict the behavior of black holes and the evolution of the cosmos, we're still just beginning. The biggest questions remain open. What is dark matter? What is dark energy? How did the universe begin? How will it end? Is there life elsewhere? Are we alone? These questions drive science forward. They inspire new generations of researchers to spend their lives studying distant galaxies, building particle detectors, developing theories, testing hypotheses. The pursuit of knowledge for its own sake, the desire to understand reality, even if that understanding doesn't immediately lead to practical applications, is one of humanity's most noble endeavors. And sometimes that understanding does lead to practical applications in ways nobody anticipated. Einstein developed special relativity to resolve inconsistencies between electromagnetism and Newtonian mechanics, not because he thought it would someday be necessary for GPS satellites. Quantum mechanics emerged from attempts to understand atomic spectra and black-body radiation, not because physicists envisioned transistors and computers. Nuclear physics was initially pure research into the structure of matter, not a pathway to nuclear power or weapons. The pattern repeats throughout history. Fundamental research into the nature of reality eventually produces technologies that transform civilization. Often there's a delay of decades or even generations between the discovery and the application. But it happens reliably enough that we should value curiosity-driven science even when we can't immediately see how it will be useful. Understanding the cosmic speed limit, the expansion of space, the behavior of matter at extreme energies, all of this enriches our comprehension of the universe and eventually feeds into technological progress. Consider photonics, the study and application of light. Because we understand that light travels at a fixed speed in vacuum and slows down in materials, we can manipulate it with incredible precision. Fiber optic cables carry information as pulses of light, transmitting data across continents and under oceans at speeds approaching light's maximum. The internet, the technology you're using right now to read this, relies fundamentally on our understanding of electromagnetic radiation and how to control it. Modern medicine uses light in remarkable ways. Lasers perform surgeries with precision impossible with scalpels. Optical coherence tomography uses reflected light to create detailed images of tissue. Photodynamic therapy activates light-sensitive drugs to destroy cancer cells while sparing healthy tissue. All of this flows from understanding electromagnetic radiation, from knowing how light interacts with matter, from the same physics that tells us nothing can travel faster than light. Even something as abstract as the cosmological principle, the idea that the universe looks roughly the same from any vantage point, has implications for how we think about our place in existence. If there's nothing special about our location in the cosmos, if the same physical laws apply everywhere, then we're not the center of creation. We're not cosmically privileged. The universe wasn't made for us. We emerged within it, products of natural processes operating across billions of years. This realization can be uncomfortable. Many people prefer to think of humanity as special, chosen, central to cosmic purpose. And in a sense, we are special. We're self-aware, capable of abstract thought, able to reshape our environment in profound ways. But we're not cosmically privileged. The universe would continue existing just fine without us. Stars would still burn, galaxies would still evolve, black holes would still merge. Our absence wouldn't fundamentally change anything on cosmic scales, yet our presence changes everything on local scales. You matter to the people around you. Your choices shape the future in small but real ways. The collective actions of humanity determine whether we survive the next century, whether we spread beyond Earth, whether intelligence persists in this corner of the galaxy. We might be cosmically insignificant in terms of scale, but we're not meaningless.
Meaning emerges from consciousness, from our ability to care about outcomes, to prefer some futures over others, to work toward goals. This is the paradox of existence. You're simultaneously a tiny speck on a medium-sized planet, orbiting an unremarkable star in a typical galaxy among billions. And you're the most complex structure you know of, a conscious being capable of pondering the cosmos itself. Both perspectives are true. Both are important.
Holding them together, feeling the tension between insignificance and significance, cultivates a particular kind of wisdom. Let's talk about one more aspect of cosmic speed limits that has profound implications: causality. The fact that information cannot travel faster than light means that events are causally separated if they're far enough apart in space relative to their separation in time. If you're on Earth and someone on Mars does something right now, you won't be able to know about it for at least several minutes, the time it takes light to travel between the planets. During those minutes, from your perspective, the event hasn't happened yet in any meaningful sense. You can't be influenced by it, can't react to it, can't incorporate it into your decisions. This creates what physicists call light cones. Imagine a cone extending into the future from your current position in space-time. The surface of the cone represents all the events you could potentially influence by sending light signals. Anything inside the cone can be reached by something traveling slower than light. Anything outside the cone is causally disconnected from you. You cannot influence those events, and they cannot influence you. There's a similar cone extending into the past, representing all the events that could have influenced your current state. The universe is structured by these overlapping light cones, a vast network of causal relationships spreading outward from every event at the speed of light. This structure is baked into the fabric of reality. It's why time seems to flow in one direction, why causes precede effects, why the universe maintains logical consistency. If faster-than-light communication were possible, this causal structure would break down. You could send messages to your own past, creating logical paradoxes. You could receive information about events before they happen from your reference frame. The consistent flow of time we experience depends fundamentally on the cosmic speed limit. Some proposed physics, like quantum entanglement, seems to violate this at first glance. When two particles are entangled, measuring one instantly affects the other, regardless of the distance between them. This happens faster than light could travel that distance. Einstein famously called this spooky action at a distance and was deeply troubled by it. But here's the crucial point: you cannot use entanglement to transmit information faster than light. The correlations between entangled particles are real and instantaneous, but they're random from the perspective of any single observer. You can only confirm the correlation by comparing measurements through classical, slower-than-light communication. It's like having two magic coins that always land on opposite sides when flipped. You flip one in New York, your friend flips the other in Tokyo, and you always get opposite results. The correlation is real and immediate, but neither of you can control which side your coin lands on, so you can't send a message. You both see random sequences that only reveal the pattern when compared later through normal communication channels. Entanglement is weird, deeply counterintuitive, and absolutely real, but it doesn't violate causality or enable faster-than-light signaling. Quantum mechanics and relativity both respect the cosmic speed limit, despite their deep differences in how they describe reality. Finding a theory that unifies them while preserving causality is one of the great challenges of modern physics. String theory, loop quantum gravity, and other approaches all maintain that information cannot travel faster than light in vacuum. This seems to be a genuinely fundamental principle, not just a quirk of our current theories. What would it mean if we discovered that the speed limit could be broken? Honestly, it would require rethinking physics from the ground up. Causality, thermodynamics, the structure of space-time, everything would need revision. It would be like discovering that 2 + 2 doesn't actually equal 4. That mathematical truth itself was different than we thought. I'm not saying it's impossible, but the evidence would need to be absolutely overwhelming, confirmed beyond any doubt, because the implications would be so profound. There have been claims over the years of faster-than-light phenomena. Superluminal neutrinos detected by the Opera experiment in 2011 caused a brief stir until it was discovered that a loose fiber optic cable was causing timing errors. Quantum tunneling allows particles to cross barriers in less time than light would take to traverse the same distance, but careful analysis shows no information actually travels faster than light. Various media can support phase velocities or group velocities exceeding light speed, but again, information and energy don't exceed the limit. Every time we look carefully, the cosmic speed limit holds. It's been tested in countless ways across vastly different scales and energy ranges, from particle accelerators to cosmological observations, and it always holds. This consistency gives us confidence that it's a real feature of nature, not just an artifact of incomplete theories. So where does this leave us? We inhabit a universe bounded by a speed limit that shapes everything from the behavior of subatomic particles to the evolution of galaxies. This limit creates a horizon beyond which we cannot see, separates events into those that can and cannot influence each other, and ultimately determines the fate of the cosmos over unimaginable timescales. It connects GPS satellites to black hole event horizons, links the glow of nuclear reactors to cosmic rays slamming into the atmosphere, unifies phenomena across 60 orders of magnitude in scale. If you made this far, make sure to give this video a like. And this other video at the left side of the screen is a must-watch. The terrifying distance to Andromeda, that dim smudge in the night sky, is hiding something terrifying about space and time. See you there.